All right, so we have already covered chapter one. All right. So, as I mentioned that primarily what we'll be focusing on defining uh, the various terminologies associated with energy. How do we split up energy into different components? Once we have split it up energy into different components, we'll try to uh, analyze the energy transfer mechanisms. And once we have the understanding of different components of energy and energy transfer mechanisms, we'll try to develop a generic equation for the energy analysis. And that would be based on the first law. So primarily three components: understanding of energy related terminologies, the mechanisms of energy transfer, and then using these mechanisms and understanding of different kind of energies to develop energy balance equation. And at the end, oh, okay, we'll move on. So the detailed overview is that first you will introduce the concept of energy and define its various forms. How do you understand energy and what are the various forms associated with energy? One of the forms is internal energy. So we'll have a detailed overview of what are the essential components of internal energy. What is internal energy made up of? Once we have done that, we'll move on towards one of the mechanism of energy transfer, which is heat. So we'll understand the initial concept of heat, the terminology associated with the energy transfer by heat, and then we'll look into the three basic mechanisms, just a superficial overview of what are the three mechanisms: conduction, convection, and radiation. You must be familiar with these three mechanisms. So we'll just have a look, a superficial overview of the three mechanisms. Another mechanism, which is that of work. How is work defined? I mean, these all terminologies are defined with regards to thermodynamics. You might have your own understanding of these terminologies, but how do we look at these terminologies in thermodynamics? This is the crux of the statement, which says the concept of work. This would not only include the mechanical work, it would include electrical work, and there would be various forms of mechanical work that we'll see. We'll try to develop equations for those various forms. Some of the non-mechanical works, we'll also just touch them. What are some non-mechanical works? Uh, Once we have understood energy and energy transfer mechanisms, we'll move on towards the analysis of system by using the first law of thermodynamics, developing energy balance equations, and which would also incorporate the energy transfer that is taking place to the system, or energy interaction that is taking moving out of the system. So all the interactions between between the system and the surroundings in terms of energy transfers, will incorporate them. You'll have a better understanding once we move on towards these transfer mechanisms. A term that will be frequently used, that is part of the flowing fluid, is other than the heat and work interactions, which are the transfer mechanisms. We'll look into the fluid flowing across a controlled surface in a controlled volume. We'll look into another term of energy transfer, which is the fluid energy. So not today, but probably we'll have a class tomorrow. So we'll have a derivation that would introduce you to the concept of fluid energy. That means a flowing fluid would itself have certain energy. How do you deal with that? Once you have done that, at the end of this chapter, you will be looking into energy conversion efficiencies. Primarily, you will define energy conversion efficiency, the basic definition. How do you define the efficiency of a system? Then we will move on towards the components that make up a power plant. So you look at the individual components of the power plant, and you'll have the efficiency of each of the component. And then you will combine those components to get the overall efficiency of a power plant. How do you define the overall efficiency of a power plant? Similarly, some of the mechanical devices you will be working on. You will work on the efficiency of pump, for instance. How do you define the efficiency of a pump? And then along with that, you'll define the efficiency of a motor. How do you define the efficiency of a motor? You'll learn. Then normally pump and motors are combined together. You'll understand the function of pump and motor. They're normally working in couple. So how do you define the efficiency of the couple, which is pump and motor? And you will also learn individually the efficiencies of turbine and generators. And I hope you know, if not, we'll clarify that normally turbines and generators are working together. We'll see the principle of turbine operation and generator associated with it. So we'll look at the individual efficiencies. and then we'll move on towards the coupled efficiency of turbine and generator working together. Clear enough? The brief overview of what we'll be looking into uh, this chapter, which is chapter 2. So let's start with a question. I have a well-insulated sealed room. Sorry. So I have a well-insulated sealed room, and by well-insulated sealed room means that there is no heat coming into the system, and similarly, there is no heat or energy going out of the system. Insulated and sealed means that there is no heat that is flowing into the system. Similarly, there is no heat that is flowing out of the system. In one of the room, I have a refrigerator with the door open, and it has been plugged into the wall, and it is drawing electricity. All right. In another room, I have a pedestal fan that is again placed within the well-sealed insulated room, and it is being electrically connected. So that means it's drawing energy out of the it is drawing the electricity out. All right. What do you expect? Would the temperature of the room rise, remain same, or would go down? Now, it would be easier for you to answer if you focus on the example of pedestal fan. What do you expect? One by one.
Temperature would rise.
Sorry?
The temperature would rise in both cases.
All right. One says temperature would rise. Anybody else? Any other opinion? Who says the temperature would decrease? What's your good name? Saad. Achha. Saad says the temperature would decrease. Nobody says the temperature would remain constant. थोड़ा सा इंक्रीज होने का मतलब मैं यही समझू कि इंक्रीज होगा. Alright. जी. आप क्या कह रहे थे? Temperature would remain constant. Temperature would increase. Now, you all have your own reasoning for that, and primarily some would say that the temperature would decrease, as mentioned, specifically when you have the example of refrigeration in mind, that it would produce certain amount of refrigeration and it would decrease the overall temperature of the room. You're not aware of the refrigeration cycle itself, how does it work? So I'll not go in detail what's the problem with that. But if you are familiar with just the first law says that energy can neither be created nor be destroyed. It can only transform from one form to another. When I look at the system, which is my room, I see that only energy that is coming into the room is which energy? Electrical energy. All right. So that is for sure, that is some energy is coming into the room and it is not being able to get out of the room. Clear? तो एनर्जी रूम के अंदर आ रही है लेकिन रूम से बाहर नहीं जा रही because you have sealed room. All right. Now, if this is the condition, have your mask on properly. So if the energy is coming into the room and is not being able to get out of the room, refrigeration or refrigerator is not a device that stores energy. It is not a device that stores energy, is it? Similarly, pedestal fan is not a device that stores energy. Clear? That energy has to be in the room somewhere. And where does it go at the end? It remains within the air of the room in the form of thermal energy. So even if I know the first law, the first impression I'll get or I should get is that energy which is coming into the room and is not being able to get out of the room, it has to get stored within the room. If the refrigerator is not storing it, if the pedestal fan is not storing it, then the only thing left to store it is the space of the room or the air of the room. That will store the thermal energy within the room. So the temperature would eventually go up. Clear? All right. As it is mentioned that if we take the room, including the air and the refrigerator or the fan as a system, which is an adiabatic closed system, the term adiabatic basically refers to well-insulated system. That means there is no heat interaction taking place across the boundary of the surroundings and the system. All right. So there is no heat coming into the system. There is no heat going out of the system. That's what adiabatic means. We'll have the revision of the term again. So in that case, electrical energy that is coming into the room would ultimately convert into the heat, which would increase the temperature of the room because there is no other device to store that energy. Clear enough? All right. Moving on, looking into the forms of energy. The general description is That energy can be in various forms: mechanical, thermal, kinetic, potential, magnetic, chemical, nuclear. And all these forms basically make up the total energy of the system. So these are all the contributors that contributes towards the total energy of a system at a given state. Clear? And normally you are not interested in what is the energy of your system at a given state. Primarily you are interested in the change of total energy of the system as it moves from one state to another. So your prime concern is what is the change in the total energy as your system moves from one state to another state. And broadly speaking, your energy is divided into two terms: the macroscopic energy. Macroscopic energy is which the system possesses, the whole system possesses this energy with reference to some outside or with regards to some outside reference. Clear? Such as the kinetic and potential energies. I'll come to it in a minute's time. What is meant by outside reference? The other form of energy is basically the microscopic energy, and it is basically the energy that deals with the molecular structure or molecular activity that is taking place within the system. So once you have defined the system, there would be molecules within the system. So what is the molecular structure and what is the molecular activity within that system? That energy is basically the microscopic energy, and all kinds of molecular activities and molecular structure that forms the microscopic energy of the system, they are defined by the internal energy of the system. So you define the macroscopic energy and the microscopic energy. Macroscopic energy is the energy of the complete system with reference to some outside center of or with respect to some outside reference, and the microscopic energy is basically related to the molecular activity. And the term defined or the term that is assigned to molecular activity or the energy associated with molecular activity is internal energy. The symbol for that is U. Normally, you represent the internal energy, which is basically represent microscopic energy by U. When I say the macroscopic energy of the system with reference to with respect to some outside reference, let's say this car is my system. If this car is my system, and it is moving at a certain velocity v meters per second. Uh, if I'm sitting in the car, with reference to me, is the car moving at a v meters per second velocity? No. So if I'm sitting within the system, the velocity is immaterial to me. Velocity of the system is immaterial to me. But if I'm standing somewhere over here, with my reference, the system would be moving at a velocity v. Now the system possesses the kinetic energy, which is the macroscopic form of energy. Similarly, if I've defined this level as my zero level, and I'm holding a ball over here, I say that the potential energy at this height is zero. If I increase the potential energy of the ball, which is my system, with reference to this level, it would have a certain amount of potential energy as a whole. So that is the macroscopic form of energy. Again, these energies are defined with respect to some outside reference. Both one is due to the velocity, relative velocity, and one is due to the relative elevation with regards to some outside reference. Let us have an understanding of what are the components that makes up the internal energy of the system. Before that, the kinetic energy of the system, you already know it is defined by half mv square. And kinetic energy is it an intensive property or an extensive property? It is an extensive property. It is dependent upon mass. But when you express it in terms of intensive property or specific kinetic energy, that is per unit mass, you will express it in small letters. Similarly, is the case for potential energy. When it is extensive property, you have the total energy. When it is intensive property, that is, you'll express it in terms of per unit mass and with small letters. Clear enough? Moving on, you have to be considerate of the fluid flowing through the system. And normally, when you are dealing with open system, you express the fluid flowing through the system in terms of mass flow rate. That is, when you have a dot on top of a dimension, that in thermodynamics would mean that you're referring to that dimension with respect to time. That means having a dot on top of it means mass flow rate, which is nothing but kg per second. That the mass is expressed in terms of rate. Clear? You can also express mass flow rate in terms of density multiplied by the volume flow rate. This could also be the expression for mass flow rate. Why? Density is what? Kg per meter cube. Volume flow rate is what? Meter cube per second. meter cube would cancel out and you'll have kg per second as the mass flow rate. Anybody has a doubt in this? All right. Similarly, it could be expressed in terms of density, which is kg per meter cube, multiplied by the cross-sectional area through which your fluid is flowing, multiplied by the average velocity of the fluid. Clear? Yes. Any doubts in this? All right. Energy flow rate again is the capital letter energy having dot on top of it. It can also be expressed in terms of mass flow rate, which is kg per second, multiplied by kilojoules or joules per kg, which is the specific energy. This would cancel out, and you would essentially have the units of kg per second, or most of the time, you'll have the units of kilowatts. So you should be familiar that whenever you are expressing kilojoules per second, that is equivalent to kilowatts. Moving on, the total energy of the system. The total energy of the system, how many components are there to the total energy of the system? Sorry? We've already learned one is the microscopic part, which is represented by U, the letter U, which is internal energy, and the macroscopic part consists of kinetic and potential energy. So if I look at the overall equation, this is the microscopic part, and these two are the macroscopic part of the total energy of the system. Is it clear? When you are expressing it in, you have mass. When you are expressing the total energy of the system per unit mass, you will have small letters representing it: small energy, small internal energy, small kinetic energy, small potential energy, all expressed in terms of per unit mass. All of them are specific values. Clear? Total energy of the system, as I have already expressed, if you're expressing it per unit mass, you will divide the total energy by mass. Now, you should be very well aware that most of the closed systems that you will deal with, they will not be having any deviation with regards to velocity or elevation. So the most of the systems that you'll be dealing with, they have zero kinetic and potential energy with regards to some outside reference. Such closed systems are basically defined as stationary systems. In such a system, which is stationary system, your potential energy and kinetic energy would essentially be zero. So any change in the energy would essentially be equal to the change in the internal energy of the system. Clear enough? So whatever change for stationary systems, which are closed systems having zero velocity and zero elevation difference, they would have any change occurring in the system of energy of the system be responsible or be equivalent to the change in the internal energy of the system, change in the internal energy of the system. Clear enough? All right. Let us have some insight of the internal energy. What are the components that make up the internal energy of the system? The components that are related to the molecular activity, that means the energies of the molecules. One is that component. The other component is basically the molecular structure, a component of internal energy which is dealing with the molecular structure. So when you talk about the molecular activities, there are generally three kinds of molecular activities that are taking place within the system. Number one is the translational energy. That means the atoms are moving at a certain velocity. The energy associated with the molecular velocity or the atomic velocity of the components within the system is basically translational kinetic energy. Clear? The velocity with which the molecules are moving within the system. Then there is rotational kinetic energy. That means that is the energy associated with the atoms which are there in polyatomic molecules that are rotating about their own axis. So that would comprise the rotational kinetic energy of the atoms within the poly. And the third is the vibrational kinetic energy. That means the atoms within the polyatomic molecules, they are vibrating at the center of their masses. These three energies, which are basically the kinetic energy of the molecules, these three energies, they basically uh, are the kinetic energy of the individual molecules that are there within the system, different kind of kinetic energy of the molecules. They comprise or they make up the sensible energy part of internal energy. So internal energy has different components. This component, which is dealing with the kinetic energy of the molecules, is basically the sensible energy part of the internal energy. And what happens is that if you increase the temperature of a system, what would happen to the molecular activity? It would go up. That means the sensible energy part of internal energy would go up. That essentially means that the internal energy would go up. Clear? So when you increase the temperature, the internal energy of the system increases. Why? Because the sensible part of internal energy is increasing. Clear enough? All right. Moving on, the other part which is related to the molecular structure, that is basically the binding forces which are there between the molecules and the atoms. and within the nucleus itself. So electrons are bounded to the nucleus. Nucleus itself has certain particles which are bounded. Atoms are bounded to the molecules. So there are a lot of binding forces within the molecular structure of the system that you're dealing with. Clear? All right. The binding forces between the molecules are they strongest in solids or gases? Solids, they are strongest. If you have to convert a solid into gas, you have to add certain amount of energy to break that binding energy and to convert it into gas. Once I have converted it into gas, that means I have provided energy to the system in order to convert it into gas. Clear? That means the internal energy of the system in gas is higher as compared to solids because I have provided extra energy to the system in order to convert it into gaseous phase. Clear? In other words, if I have to do a phase change process, put it into gas, I have to overcome this binding energy. So the energy which is related to the phase change of the system, that means the energy required to overcome the binding energy of the molecules in order to convert it into another phase. That is the phase change part or phase change energy of the internal energy. So internal energy once had the sensible part, which is related to the kinetic energy of the molecules. The other part is basically which is associated with the phase change of the system. Clear enough? Is this part clear? So gas would have a higher internal energy because you have added energy to the system in order to convert it from liquid to gas. And this part is basically the internal energy of the system, which deals with the phase of a system and is called the latent energy of the system. Clear? So one was the sensible energy, which was dealing with the kinetic energy of the molecules. The other is the latent energy part of internal energy, which is dealing with the phase change process. The other two parts of the components are the chemical energy of the system, or the part of internal energy which is defined as chemical energy. But chemical energy only comes into play when you have a chemical reaction taking place. That means bonds are breaking up and new bonds are forming. So whenever you have a chemical reaction taking place, internal energy of a system is changing because the chemical energy part of internal energy is changing. Clear enough? Similarly, the fourth component is the nuclear energy. Nuclear energy is again the component of an internal energy. When you have a nuclear reaction taking place, that means there are changes that are taking place within the nucleus of the system. Only then that part of internal energy comes into play. Clear enough? All right. Moving on, the total energy of a system can be contained or stored in a system that if the total energy of the system is contained within the system, that is stored within the system, it is the static part of the energy. Clear? Energy that is inherently within the system. The other form is the dynamic form of energy. That means the dynamic form of energy is not stored in the system, it is coming into the system and going out of the system. All right. This is basically the energy that or energy interaction that is taking place at the boundary of the system as the energy cross it. That means energy could be gained by the system as a result of this interaction, or energy could be lost by the system as a result of this interaction. So dynamic energy interactions basically could add up the energy of the system or could result in the reduction in the energy of the system. Clear enough? The two sorts of energy interactions which are very common and that are dynamic forms of energy interactions, they are heat transfer and work. So these two interactions are basically the interactions that are dynamic forms of energy. And when you have to define the two, we'll look into detail. But as for a general understanding, the difference between heat transfer and work is that if an energy interaction is taking place due to the temperature difference, that is basically heat. All other sorts of energy interaction, dynamic energy interactions would be associated with work. Clear enough? Now, one thing important over here is that we have discussed two kinds of kinetic energies. Kinetic energy of the system as a whole with respect to some outside reference, or kinetic energy of the molecules. You need to differentiate between the two. It says that distinction should be made between macroscopic kinetic energy, which is with respect to some outside reference, and the microscopic kinetic energy of the system, which is the sensible energy part of the internal energy of an object. And how do you differentiate between the two? You say that the kinetic energy of an object, if it is organized and there is orderly motion of molecules in one direction or around axis, this is basically the macroscopic part of energy or macroscopic kinetic energy. The random and highly disorganized motion of molecules that makes up the kinetic energy is basically the microscopic kinetic energy. And we are normally interested in organized form of kinetic energy. How? Let's say we have this dam, there's water molecules over here. If we place the wheel in this region, the molecules are having random kinetic energies. That is, they have the internal energy, but in the microscopic form. This would not turn the wheel placed within the region. But if you organize the motion of molecules in such a way that they hit the wheel in a certain direction, they have an organized, orderly motion. This motion would essentially be resulting in the macroscopic kinetic energy of the system. Organized, orderly motion resulting in the work produced as a form of macroscopic energy, which is the kinetic energy of the system. Clear enough? All right, I'll stop over here.